Now this question has an equation which is not y in terms of x, but instead x in terms of y, and we call this type of equations implicit differentiation, which can be a mixture of x and y or x in terms of y. So the first thing that we have to understand in implicit differentiation is how it works. The main concept is d by dx of y is dy by dx. So that is the main idea. So we know d by dx of tan ax is sec squared ax into chain rule d by dx of ax. But if it is d by dx of tan ay instead of ax, it would be sec squared ay times d by dx of ay, which is going to be sec squared ay times, now d by dx of ay is a, dy by dx. So this implicit part is going to have a dy by dx with it. That is the main idea. So first of all, let's find the gradient of the curve, because after all, to find the equation of a normal to the curve, this is from C1, we need to know about the gradient of the curve, because if you remember C1 review, equation of a line is if a line passes to the point x1, y1 and it has a gradient of m, then the equation of the line is y minus y1 equals to m x minus x1, regardless of what type of line it is, normal line or parallel line. That's the equation of the line. Now the gradient rule for a normal line is gradient of normal. So gradient of normal line is equals to minus 1 by dy by dx, meaning gradient of the curve at that particular point. So these are the two things that we need to know. So let's start with this. So first of all, we have x equals to 2 tan. Let me call this entire paraphernalia, entire mess of an angle, theta. So 2 tan theta. So if we differentiate both sides, it would be d by dx of x on this side and d by dx of x on the other side. So 2 tan theta y plus pi by 12. So d by dx of x is 1 and d by dx of 2 is 2. Tan theta is sec squared theta times the chain rule, which is d by dx of the angle, which is y plus pi by 12. So this is going to be 1 equals to 2 sec squared y plus pi by 12. Now think of this as a constant, because 12 pi by 12 is a constant. So d by dx of y is dy by dx. So now what we can do is we can send this sec squared to the other side. So this would be 1 divided by 2 sec squared theta equals to dy by dx. Now since we know how to calculate cos squared but not sec squared, so what we do over here is we can write it as half. Now sec squared reciprocal is cos squared. We can write cos squared y plus pi by 12. So we got an expression. Remember, this is not the gradient of the curve. It's the derivative of the curve, an expression for the gradient of the curve. So we have to put the value of y coordinate pi by 4. So let me put it over here. So at y equals to pi by 4, dy by dx equals to half cos squared pi by 4 plus pi by 12, and that turns out to be, so 1 by 4 plus 1 by 12, that is 1 by 3. So pi by 3 is 60 degrees. So this is half cos squared pi by 3. Now cos 60 degree is half. So this is going to be half into half squared. So this would be 1 by 4 into 2, 1 by 8. That is the gradient of the curve. So now gradient of the normal is going to be minus 1 by dy by dx. So gradient of normal equals to minus 1 by 8, which is minus 8. Now we are going to use the equation of the general line y minus y1. This is known as the point slope form of the equation of the line. Y minus y1 equals to mx minus x1. But we need to know the y coordinate, the x coordinate. We know the y coordinate is pi by 4. We need to know the x coordinate. So let's find that out. So at y equals to pi by 4. So let's put it in the equation. So x equals to 2 tan pi by 4 plus pi by 12. So it is 2 tan pi by 3. So tan pi by 3 is tan 60 degree. Tan 60 degree is root 3. So this is 2 tan root 2 root 3. So now equation. So equation of the normal. So y minus y1, which is 2 square root 3, equals to m, which is minus 8, x minus x1, which is, no, this is, let me correct this. Y is pi by 4, so this will be y minus pi by 4, and x minus 2 square root of 3. So that's the equation. Now if you want to simplify it, you can, but in this particular question they didn't say that you have to give the answer in a particular format or simplifying, so keep it this way, it's alright.